Thanks for Chair's kind introduction. So I'm Qingdong. I just joined the Macau University of Science and Technology 2 years ago. So probably some of you might be surprised, right? Macau also has higher education. I was surprised too. Right? I didn't hear of any university in Macau. Macau is actually very, I can say it's a super small or super big city in China. Small because the land area of Macau is even smaller than an airport, the Shanghai Pudong Airport. But super big, I mean the casino industry is the #1 in the world. I think it exceeded the revenue of Vegas, right? No, Vegas, yeah. The Vegas in 2 years ago, I think, yeah. So it became #1. So our financial support actually from the world, right? So the revenue are actually from the gambling industry. So yeah, thanks for all of you guys. And the interesting thing is that I think if you hold an overseas passport, you don't need a visa to enter Macau. But for our Chinese, we need a certificate, So you can go there anytime if you want. So I changed the title a little bit to structurally engineered MO3 material for anisotropic phonon polaritonics, because our recent focus is mainly on the structural engineering of these van der Waals materials. My research background is on the material science and engineering, so I mostly play with these van der Waals materials with some chemical method or nanofabrication from those kind of perspectives. That's why sometimes the reviewers will comment that you don't have too much physics, okay? Yeah, this is the outline. I will try to overview our recent progress based on the materials engineering perspective. Okay. So mainly about the hyperbolic polaritonic photonic crystal, kind of, but based on the in-plane hyperbolic phonon polaritons in MO3. So next one is the monolithic planar lens. We developed a RE method to thin down the van der Waals crystals, individual crystals. We use photolithography to cover part of the individual crystal and then do RE etching. We can precisely control the layer numbers of MO3. I think it's first demonstration because I never saw such kind of experiment. So the last one is a canalization lens. I think Professor Chen Weishu also mentioned this experiment. So I will introduce a little bit. It's still under review. I think this image you have already seen a few times, but it's a good start for introduce polaritons in van der Waals materials. They have many advantages, right? Like the high light confinement, and it can be tunable. You can easily create van der Waals heater structures by stacking multi-layers. But actually, polaritons, I just want to mention that polariton concept is not new. I'm not sure if you all know that. It's actually first proposed by Kun Huang, a Chinese physicist, in 1951, a Nature paper. Okay, so I just mentioned that, the history. Yeah, so why polaritons in 2D materials are interesting? I think the first real space observation of these plasmon polaritons in graphene also has already demonstrated that merit because it can be electrically tunable, which cannot be achieved in traditional metal plasmonics, right? And the loss in these natural crystals is also very low compared to metal surface or metal plasmonics. The loss can be even lower in phonon polaritons because there are no plasmonic scattering, electronic scattering in phonon polaritons. So quite a few nice work, including the isotope doping. This MO3 is the main material I played with, as Rainer also introduced. It's an in-plane hyperbolic material. Also have in-plane elliptic dispersion as well. For example, if you see that at specific wavelengths, the polariton fringes only propagate along one direction, right? So this is an anisotropy lies in. Yeah, I actually did my PhD in this group, in Qiao Liangbao's group, and this paper is collaborated with Rainer Hebrand and Pablo. Yeah. If you further see the anisotropy in MO3 material, it's disks, right? So in graphene or H-band isotropic crystals, you will see such kind of circular spreading of the polaritons. But in MO3 disk, you will see such kind of elliptical or hyperbolic shapes. Yeah, this work was did in my postdoc in Australia, in Monash University. It's collaborated with Cheng Wei-Xiu's group and also Alu's group. We did these twisted bilayers and then image this topological transition of phonon polaritons. So very interesting physics. I'm not going to doing too much because today's topic is on structural engineering. But van der Waals history structures, we have done a few works actually. This is another one. We place graphene on top of the MO3 crystal. I think there are quite a few same topics papers online in that same time. So we are just one of them. We also did this kind of 2D, 3D heterostructure with silicon carbide. Silicon carbide also has a phonon polariton band within the overlapping with MO3. So we can basically switching the hyperbolic dispersion in original MO3 to the orthogonal direction. Yeah, switching to the 90-degree switching. Recently, we got a invited review on NPJ Nanophotonics, which is a new journal. So we summarized this in-plane hyperbolic phonon polaritons in these emerging crystals, but not all of them are van der Waals materials, but it could be interesting. I think it will be online several days later. As we did a lot of manipulation strategies to tune this in-plane hyperbolic material, so we also summarized a few manipulation strategies in this review. We discussed from the materials point of view and the physical stimulation and also dielectric environment, as well as some polaritonic interactions. If you are interested, you can look into that. Yeah, so this is the current focus of my research with this in-plane hyperbolic polaritons. I think, although you might feel that the grating design is quite simple, right, for a conventional isotropic material, but it's quite interesting if you are doing this simplest grating with in-plane hyperbolic polaritons. For example, we use a optimized FIB technique to directly pattern these different orientated gratings on top of the flake, and you can basically see the excitation of phonon polaritons with different propagations, and the near field images matches quite well actually with the FFT in the K space, which also matches well with theoretical simulations done by Professor Cheng Wei-Xiu's group. And then we thought about that, can we extend that kind of momentum matching between the grating vector and the hyperbolic dispersion to a 2D space, like 2D array? Then we did such kind of fabrication, still using the FIB technique. Yeah, so the point for this kind of photonic crystal and hyperbolic dispersion can be clearly seen here. The momentum matching between the lattice vector and the hyperbolic dispersion determines the mode excitation of this kind of hyperbolic crystals. So that's I think that's the main point of these photonic structures integrated into in-plane hyperbolic materials, you need to consider such kind of momentum matching between the nanostructure vectors and also hyperbolic dispersion. There should be some momentum matching. Then it will be exciting the phonon polaritons or photonic modes. Another thing is, with this in mind, then we can exactly assign these Bragg resonance peaks to those modes excited in the photonic crystal, right? So yeah, that's quite. It's a kind of a correlative analysis. I think it's quite good. But what's more for this hyperbolic crystal, I think this characteristic is kind of more beautiful, I think, because for a graphene photonic crystal or H-beam photonic crystal, they are kind of isotropic, right? So they don't have such kind of robustness against lattice rearrangement along the hyperbolic forbidden direction. So this figure is actually the resonance peak shift when you're changing the period of the photonic crystal. So for an isotropic material, the resonance peak will definitely change with the period variation, right? But for our hyperbolic one, if you change the period along the hyperbolic forbidden direction, that's 0.001 direction of MO3, you see the resonance shift did not change. So it remains as a constant, kind of a constant. And this is a simulation we did. For example, if you are using a square shape arranged photonic crystal with this diamond-shaped arranged photonic crystal, the resonance peak did not change. And if you are changing the period within a range, and the resonance peak just remain constant. Yeah, this is I think it's a new feature of hyperbolic polariton-based photonic crystal. Because in conventional bulk crystal using silicon or van der Waals photonic crystal using H-beam, the resonance, the Bloch modes of photonic crystal all relies on the lattice orders, right? Yeah, so this is the difference between our hyperbolic crystal with conventional isotropic crystal. And yes, twist is always a merit of this in-plane anisotropic crystal, so we can fabricate photonic crystals with different orientations with respect to the crystal directions. Then we can have such kind of rotated mode distribution within this material. And this is an experiment, simulation matching quite well, and also the FFT directly from the experimental near-field images. So I think it's matching quite well, and it can be correlated with the far-field FTIR spectra, which peak can be assigned to which modes. Yeah, so quite nice. This work is another work we developed a reactive ion etching method to deal with this van der Waals material. Because FIP, using a metal ions to do the myoning. So there might be some ion implantation or damage to the crystal, but using a gas phase reaction ion etching method, we can quite nicely thinning down the material. For example, you can see here, this is a higher thickness. We use photolithography to protect this area, and then using RE etching to reduce the thickness of MO3. Yeah, the surface is quite flat, so kind of a layer by layer thinning. But obviously, some reviewers did not like our idea we originally submitted to Nature Photonics. So in this work, we try to convince the reviewer that for conventional free space light, if you want to achieve focusing or refraction, right, you need two different refractive index. But in our hyperbolic polaritonic materials, you don't need two different kind of materials, right? So same material with different thickness can achieve refraction and focusing. Yes, here's our experiment and the fabrication. So we use photolithography to define some angled interface. We can use a larger thickness here, lower thickness there. We can also reverse the fabrication. And you will see the refraction direction is kind of different. That is because of the non-collinear of the wave vector and the Poynting vector, right? I'm not going to too much physics. If you are interested, probably you can see our paper. I think it will be online this week or next. We also can change the shape of the interface to resemble the conventional lens. And if we change the thickness, we can get the different focal spot lengths in terms of the difference in the radius of this circular interface. We also try to do some more difficult, right? We tried to fabricate such kind of gradient-shaped van der Waals interfaces so that we can achieve some transformation optical devices like this kind of Leeuwenberg lens and fisheye lenses, but we failed. Okay, so might need some optimization, and if you have a way to do it, we are happy to collaborate. The last one is about the recent progress on canalization lens using MO3, which is a biaxial crystal for imaging and different from uniaxial crystal based on HBN, right? So in this biaxial crystal, we found in a single layer of this material can achieve multiple canalization regions in 3 directions, actually. In Z direction, X direction, and Y direction. This is simulation images, cross-section simulation. If you place MO3 crystal on top of 2 closely packed disks with a narrow gap like 50 nanometers, we can clearly see the directional propagation of phonon polaritons, and at the top surface of MO3, you can clearly resolve that kind of narrow gap. And it can be achieved in 3 directions. Yeah, this is work we first use a gold disk resembling the HBN imaging. But there are some like Humble. If you play a flake on top of this gold disk, right? So next we are trying to push the limit of the narrowest object by using FEEP to get a 15 nanometer width of gold line. And by extracting some line analysis, we can resolve that kind of extremely narrow objects. So that demonstrates the capability of MO3 for imaging device. Yeah, so I think we are doing polaritons in 2D materials, and people also always ask us about the application of the material, and we try to make a small step, but yeah, the reviewers question us, there's no new physics there, so a lot of rejections we received. But I think for this material, we definitely can use it for, in some way, or in some cases, we can use it to image some nanoscale patterns when we place the material on top of that pattern, yeah, in some way. This is a demonstration of to image a buried nanocircuit, like a CPU pattern. Yeah, this is a SEM image. We deposit silicon oxide on top of it. Yeah, just bury it and then use MO3 on top of it to do the imaging experiment. I think it's quite nice. And we can using FIB to artificially make the cut. And then we see some contrast there because we just say that this material can image up to 15 nanometer width, right? So the imaging capability is quite good, excellent. Yeah, so here comes the summary. I introduced the structural engineering of this material to do hyperbolic polaritonic grating and photonic crystals, and also by using IE method to do a monolithic stepwise lens, which is quite good for this kind of in-plane hyperbolic wave-guided mode. Phonon polaritons. So the last one is another application example using canalization effect to do near-field imaging. Yeah, so in the last, I want to thank my collaborators, especially Professor Chen Weiqiu. He gives me a lot of support. Also the financial support from the Macau and also Australian fundings. Thank you. Thanks.
Thank you very much for the nice talk. So we have time for one quick question. Any questions from our audience? Okay.
Very nice talks. What's the depth you can probe with the last thing you demonstrated? Is it through MO3 and what's the thickness?
In the theoretical calculations, we're using 500 nanometer. But in experiment, we are using 250 nanometer. But I think it can be thicker but might get a compromise in the resolution. Yeah, so because if you are in the canonization region, theoretically the ray of photon polaritons could be very straight. Yeah, yes. So the canonization is the main point of this kind of lens. I think this theory has already been I think 20 years ago, like using canonization effect to do self-resonance imaging. But in years ago, they are doing with metamaterials, right? Now we are having natural material, yeah.